So this model, this result of median voter theorem was first proposed by Downs, an economist named Downs, in 1957. That's why this kind of result is, this kind of models are called Downsian model of electoral competition. Electoral competition. Now, and Downes's idea was that in this kind of electoral competition between candidates who only care about winning elections and can commit to their announced platforms, will result in both candidates announcing something in the middle and announcing the median policy. Okay, and these kind of insight actually generalizes to other kinds of competition which are not necessarily related to elections. Okay, so let's talk about this kind of sort of model. So consider again a line, but this time instead of interpreting it as an ideology of voters favorite policies or ideologies left to right, consider it as location on a street. So consider this line as a street. Okay, and then instead of voters, consider buyers located on various points on the street. So these are location of buyers. Okay, and instead of candidates, think about two shops who want to locate them, so who are deciding where to locate within on the street. Okay, to locate to the left, to the right, to the middle of the street. Okay, so there are these two shops which are the sort of equivalent of the candidates in this in the previous version of the model, who want to locate on the street. Okay, so suppose there is a shop A who is located in LA. LA is the location of A. Okay, and suppose there is a shop B which is located in LB. Okay, now by the same logic as before, all the buyers now, so what is the motivation of buyers to choose between going to shop A or shop B? There, for them, distance is costly, so they want to go to the shop which is nearer to them. Everybody goes to their local grocery shop, right? So all buyers will look at the locations of the two shops and choose to go to the shop which is nearer to them. So again, by the same logic as before, all the buyers who are located to the left of shop A will go to the shop A. All buyers which are located to the right of LB will go to shop B. Okay, because they are nearer. And then for the shops in the middle, they'll for the buyers in the middle between LA and LB, they'll again look at which shop is nearer and go to that shop. So again, there will be a midpoint like here, and all the buyers to the left of that midpoint will go to A, all the buyers to the right of that midpoint will go to B. Okay, and then that will determine how many buyers are going to A and B. Okay, so suppose we have this distribution of buyers over this location. Okay, and then all these buyers to the left will go to A, and all these buyers to the right will go to B. Okay, and the objective of the shops is to maximize the share of buyers going to their establishment. Okay, and again, applying the same logic as the median voter theorem, you can show that locating both shops locating themselves in the median of the buyer's location distribution. So LA equals to M, LB equals to M, where M is the median of buyer's location distribution is the Nash equilibrium. It's the only Nash equilibrium. So this is the only Nash equilibrium of the game. So you see that when our shops are competing for buyers, they tend to locate themselves both all at the same point, which is sort of in the middle of the neighborhood, okay, or middle of the street. So this explains, for example, why you find shops which are sort of clustered around one point, right? Which we tend to call sort of the marketplace, where all the shops are located. In a neighborhood or even in a city, say all electronic stores located in one cluster, all hardware stores located in one cluster, all furniture stores located in one cluster. So these kind of real life phenomenon can be explained by models like this, okay, using this concept of game theory and Nash equilibrium. So this was first the insight, this specific firm location model was first the insight of this economist called Hotelling, and that's why this result is called Hotelling's lemma, which is sort of the equivalent of Downes's median voter theorem. So and this sort of constitutes this one class of interesting models where game theory can be applied to understand real life phenomenon like behavior of politicians or firms. Let's move to the second application. In the second application, we will work out a model of crime and police. Okay. So this is a two-player game. What are the two players? The criminal and the police or the government. So it's a two-player game. The first player is the criminal, C, and the second player we'll call government or the police, G. Okay. So these are the two players. What are their strategies? So criminal strategy is to decide how much crime to commit. So C's strategy is to decide how much crime to commit. This is denoted by a number x, which is a non-negative. So higher the value of x, higher is the amount of crime committed by the criminal. So x is decided by C. What is government strategy? Government strategy is to decide extent of law enforcement. Extent of law enforcement. It is denoted by Y. Okay. So actually let me switch this. It would be better because that's how sorry, I wrote the same thing again. So let's make criminal strategy Y and let's make government strategy X. Okay, so higher the value of X, higher is the extent of law enforcement by the government, and higher the value of Y, higher is the amount of crime committed by C. So these two are the choices, the strategies of the two players. Let's now consider payoffs. These are the payoffs. So first I've already the payoff of the government written. UG is given by minus x c to the power 4 minus y square by x, where c is some positive number, constant, it's a parameter. Why c to the power 4 rather than just some number, other constant c? That's, you'll see that having this c to the power 4 expression helps us later with the calculation. Okay. The interpretation of this parameter c is the cost of crime. So higher the value of c, higher is the cost of crime for the criminal. Okay. Now this, therefore, you see in the payoff of the government, it not only depends on x, which is the strategy of the government, it also depends on y. Let's go back. Yeah, it also depends on y. Okay, so higher the value of y, which means higher the amount of crime committed by the criminal, you have a lower payoff of the government. Okay, so government's payoff goes down if the criminal commits higher level of crime. Okay, but if x goes up, then the first term goes down. From the first term it says the payoff goes down, but for the second term the payoff goes up. So the same y, if x goes up, the second term goes down, right? So the payoff goes up. So it's because it's a smaller negative number. Okay. What is the payoff of the criminal? Payoff of the criminal is given by root y divided by 1 plus xy. Okay. Again, you see the payoff of the criminal depends not just on the action or the strategy of the criminal y, but also on the law enforcement strategy of the government x. You can think of this as, suppose criminal commits crime of quantity y, root y is the payoff of the criminal conditional on not being caught. Okay, so suppose 1 by 1 plus xy is the probability that the criminal doesn't get caught. So the expected payoff is 1 by 1 plus xy, which is the probability of not getting caught, times the payoff from the crime, which is root y. With the rest of the probability, you get caught and your payoff is 0. So that's why there is no other term, right? So that's how to interpret this term. Okay, so these two are the payoffs. So now what would they do? So now notice that UG, government, only controls x, okay, and the criminal only controls the y. Okay, but their payoff depends on the strategies of the others. So this is like a Kuruno kind of a situation where one player's payoff depends on that player's strategy as well as the other player's strategy. So in this case, what to do? Again, you apply this sort of idea that you have to find best responses. So when G decides what is the amount of law enforcement X to choose, he fixes some value of Y. So for some Y, for any given Y, he needs to find out, government needs to find out what is the optimal X. Okay. Similarly, for the criminal, for any given X, the criminal needs to find out what is the optimal Y. Okay. So let's do that. So for the government, for any given level of y, it decides x by maximizing UG, right, with respect to x by fixing some y. So government optimizes this. It uses x to maximize UG for any given level of y. So fixing some value of y. So if you do the optimization, you will get that UG. So this is UG. So if you do the optimization, what will you get? First order condition, you get that minus c to the power 4 plus y square by x square equals 0. From this you can write that x is y by c square. This is the best response function of the government. So government's best response is, which depends on y by c square. That's the best response function of government, right? So for any given level of y, this is the optimal amount of x that the government would choose. Similarly, I can do the same thing for the criminal. So the criminal also maximizes UC subject to y by fixing some level of x. So what is UC? UC is, I'm just writing it here again, root y by 1 plus xy. If you take the derivative and do the first order condition, you will see that it is 1 plus xy square half y to the power minus half times 1 plus xy. So this is the derivative of the numerator times the denominator minus derivative of the denominator, which is x, times the numerator, which is root y, equals 0. If this is 0, the denominator is a square term which is positive. That tells you that half y to the power minus half times 1 plus xy equals xy to the power half, which tells you 1 plus xy equals 2xy, which tells you xy equals 1, which tells you y equals to 1 by x. This is the best response function of the criminal. Oops, sorry. So best response of the criminal, which depends on x, is just 1 by x. So now you can find out the Nash equilibrium. For Nash equilibrium, we need mutual best response. So I have y equals 1 by x and I have x equals let me check, y by c squared. Sorry, y by c squared. From this we get that y equals c, and hence x equals 1 by c. So this is the amount of crime and law enforcement that will happen in equilibrium. So this is basically solved the way Cournot equilibrium is solved, right? Because these are continuous strategies and the payoffs depends on not just your strategy but also your opponent's strategy. And so basically you go to the you compute the best response function by maximizing payoff with respect to own strategy, fixing the opponent's strategy. So this gives you this best response function for the government. Similar exercise gives you the best response function uh, for the criminal, and again for mutual best response you just solve the two equations and get the Nash equilibrium. So this is the Nash equilibrium of this game. Okay, so, and this tells you that higher the C, the greater is Y. So Y is, again, just to go back, Y is C's criminal strategy and X is government strategy. So higher C means higher is the amount of crime committed by. So higher C higher means Y star is also higher. So higher is the crime committed by the criminal, and lower is the enforcement. So 1 by C becomes lower, so lower is the enforcement by the police. Okay, so as the cost of crime goes up, the enforcement goes down and the crime goes up. Okay, so that's the idea. So this concludes the second part of the sort of second section of the application. Okay, so let's stop here, and in the next class, depending on how this goes, we will move into a new concept. Hopefully this was understandable. In case you have problems, we will discuss this over an online platform that I'll give the details about. Okay, thank you.